Okay, this is video number 2 in the refraction series of videos. And this video is connected with something called Snell's law. You need to know Snell's law. You don't need to know this bit, but Willebrod Snell. I think he was Belgian, and he did some important work back in the late 1500s and early 1600s. I think that was his birthdays and death days, years. So he did this quite a long time ago. So this is quite an old bit of physics, and it's all to do with how light changes direction when it goes from one material into another. You don't need to know that bit. Probably spelt his name wrong. Never mind. Okay, so what's Snell's law all about? We've already looked at, there's our air, here's our glass, for instance, a different medium. We've got our normal line, we've got a ray of light coming in, and we know that when it slows down, it turns and bends towards the normal. We've got these angles, θ1, θ2. If you don't know what I'm talking about, you're looking at these videos in the wrong order, because all this was covered in video 1. What Snell did was he had a block of glass and he had a beam of light, and he shone this into the glass, and he measured the angles. Excuse me. He measured these angles, and he was trying to find a relationship between the two angles, and he plotted a graph. And I'm just going to go and have a quick look at what the graph looks like, because I want to get this right. And he got a graph of angle in air, which is θ1, and he got angle, it could have been in water, could have been in air, doesn't matter. Could have been in water, could have been in glass, it doesn't matter. Angle in material or medium, which is θ2, and he started off with 0 degrees. 0 degrees is where the ray of light would come in here, and if it comes in here along the normal, it continues along the normal. So we've got our first point of the graph starts here, and he got a graph that did, well, it went up to 90 degrees, and this goes up to 90 degrees here, and he got a graph that did this, which in physics isn't much use, because what we want in physics is a law, and a law is a relationship that matches our two variables, and we really want a straight line. So he had a bit of thought about this, and he thought, well, what else could I do? Because I really want a straight line. I don't want a graph that curves like that. If I plot θ1 and θ2 in degrees, that's not going to give me a physics relationship. So what Snell did, he messed about, and he knew it was to do with angles, and what he did was he tried a little bit of trigonometry, and he actually plotted second time round. I don't think this was necessarily second time round. I think it took him a long time to work out how to get a straight line graph, and he actually found that if you plotted the sine of this angle against the sine of this angle, if you plot sine θ1 against sine θ2, you actually do get a straight line, and therefore you have a relationship. And the good thing about a straight line is you can find the gradient, and you know that the gradient of a line can be worked out by using the formula m equals y2 minus y1 over x2 minus x1. That will give you the gradient. You could do it the other way up, it doesn't really matter, but what we want is something that gives you a relationship between the two, and the gradient M would be that there. Okay, I'm just going to go back and check my notes. Pretty sure that's right. Yep. Okay. Sine theta 1 over sine theta 2. And the gradient actually is equal to the refractive index. Now, the refractive index doesn't have the letter m. M is just a general letter for any gradient of any graph. But in this case, the letter for the gradient, the refractive index, is actually the letter n. Okay, so what we can do is we can take this information from the graph, from Snell's law graph, and we can say that the gradient n is equal to sine theta 1 over sine theta 2. And that actually is the first part of Snell's law. And I say the first part because we're going to continue and use this formula in a number of different ways. So n is the refractive index. And theta 1, or sine theta 1, is the sine of the angle in air. And theta 2 is the sine of the angle in the material or the medium. And that is actually what Snell's law is. Okay, so if you wanted to work out what sine theta 1 is, if you knew that this was 40 degrees, for instance, you can put 40 degrees into your calculator and press the sine button, and you'll get the sine of the angle. You know how to do this from maths, how to get the sine of an angle. Right, some important notes. Don't forget, if you can't keep up with me and my writing, you'll have to pause the video and get the stuff written down. So some important points or important notes. N is a number that lies somewhere between 1.0 and 3. So n is bigger than or equal to 1, but is less than or equal to 3. So it depends on how dense your material is. We've already been through this in the first video. Air has a refractive index of 1. Diamond has a refractive index of 2.42. And we normally work to 3 decimal figures. So if you look up the refractive index of diamond, 2.42, we ought to say that the refractive index of water is 2.26, the refractive index of glass 1.50. Now n, that's 0.1, so it's a number. It doesn't have any units. That's the second point. It's just a pure number because it's a ratio. Doesn't have units. And number 3, it needs to be written to 2 decimal places. Okay, so you'll find these in the data table with a list of materials. But I'm going to record them here so you can write them down, so you don't have to keep changing screens and going off to find a data table. So air, 1.00, water. Did I say 2.26 before? That was rubbish. That was actually the speed of light in water. So ignore what I said earlier, complete garbage. that ratio of 3 times 10 to the power of 8 and 2.26 times 10 to the power of 8, which is the ratio of speeds in air and water. The reduction factor, that's 1.33. Glass, 2. I'm not doing very well here. 1.50, and diamond 2.42. I think I referred to diamond as being around about 2.4, and whilst I was away after doing video 1, I went away and checked it, and it is in fact 2.42, which I thought it was. So there's a list of refractive indices. Letter N, no units. Okay, 2 decimal places, and all the values for refractive index lie between 1 and 3. The denser the material, the higher the refractive index. The higher the refractive index, the more the light is bent away from the normal when it goes into the material. Okay, so what can we do? You could actually do an experiment, and if you were in school and we were all together, you can do an experiment, and you can set up a block of glass that looks like this. So here's just a little bit of an experimental detail. And normally when we do this experiment, we use what's called a semicircular block. And you might have seen these before. Here's our normal line. You get the block of glass, you put it on your whiteboard, and you're going to shine that red beam of laser light. I think you've all done this before. You shine your red beam of laser light into the block of glass, right into the middle of this semicircular block. So in the center, in the middle of this line, here it comes. Here's your air on the outside. Here's your glass, possibly perspex, but it's got a refractive index which is very similar. And then the ray of light comes along here. Now this is of interest because this semicircular surface, it doesn't matter. I'll just draw a couple of other lines. If we have a ray of light coming in at a different angle, over here for instance, the ray of light is going to travel differently in this part of the glass here, but wherever the ray of light that is refracted goes inside the glass, because this glass is semicircular, it always hits this curved surface at right angles. Now if it hits that surface at right angles, it just comes straight out, and it makes it much easier rather than having the block like that, where the ray of light comes in and it changes direction once and it changes direction twice, and then we've what angle are we measuring? There's only 2 angles we need to measure when we use a semicircular block. You can do it with a rectangular block, but it's easier. So we use this semicircular block. The ray of light will always come out in a straight line, and then we're going to measure θ1, and doesn't matter where all these lines are, θ2. And what we do is we change the direction of the beam of light, and you can start there at 0, and you can keep increasing the angle possibly in 10-degree steps, and you keep going and you keep going, and then you build up a table. You build up a table of θ1 and θ2, and if you were to plot θ1 and θ2, as I mentioned earlier, you'd just get this graph that goes off and ends up in a curve, and that's no use. So we then change our table into sine θ1 and sine θ2. We then plot sine θ1 against sine θ2. We get a straight line, and by measuring the gradient of the straight line, we can find the refractive index of the material. So this is an experiment to find the refractive index of a bit of material, of a medium. So if you wanted to put a title to find the refractive index of a material, that would be your experimental title. I suggest you do that. Title. There's your title. You'd do a method. You'd have a diagram, and you'd label this up air, glass, and you can put in your beam of light. And I suggest you copy this down quickly. So you set up your semicircular block on a board, just like this. You've all used these boards before. You shine the beam of light into the material. You measure the two angles, theta 1 and theta 2. So your method would just say exactly that. Set up a block of glass, shine a beam of light into a material, measure the angles theta 1 and theta 2, plot draw up a table of theta 1 against theta 2, draw a graph. The graph gives you, not quite like that, but the graph gives you a curve. And then if you do a second graph, so that's graph 1, theta 1 and theta 2, the second graph of sine theta 1 against sine theta 2 gives you a straight line, and the gradient is the refractive index n, and you can do that y2 minus y1 divided by x2 over x1. That's an experiment you would usually do in school, but you're not in school. So I'm just telling you. So title, diagram, method, change theta 1, measure theta 1 and theta 2, make a table, plot a graph. Graph does not give you a straight line. Second table, sine theta 1, sine theta 2, plot a graph. The graph does give you a straight line, and the gradient of that straight line is the refractive index. So there's the details of Snell's law, how to find Snell's law. N equals sine theta 1 over sine theta 2. So I suggest you pause the video there and do this title, then do a diagram, which we've got. Then say your method, and I'll say it again for about the third time. Set up the equipment as shown, shine a beam of light into a block of glass, measure theta 1 and theta 2. Then number 1, plot a graph of theta 1 against theta 2. That would be your results. The only thing is you're not getting any results. I'm not giving any results. I'm not asking you to plot a graph, but that's what you would do is table 1 and graph 1. You would then say that does not give me a straight line. So this is all in your results, if you like. That does not give you a straight line. So go away and do another table of sine theta 1 against sine theta 2, plot those two values, gives you a straight line, measure the gradient. That is the refractive index. Hence, you arrive at Snell's law. So that's the experimental detail of what you would have to do. And you can pause there and write that up if you wish to pause, that is. Okay, because I didn't write everything down there. What we're going to do is have a look now at some examples, some calculations where we're going to use Snell's law. And you might get a diagram like this. This is air, and we know air has a value for its refractive index is 1.00. And if you can do this experiment, great. In fact, don't do it. Take the money and run. Sell the diamond. N is equal to 2.42. And we've got a beam of light coming in at an angle of 10 degrees. And it goes off at some angle that we don't know. We know that this angle in air is called theta 1. We know that this angle here is called theta 2. So the first question is calculate the angle theta 2, which is the angle of light, the angle of the light in the diamond. Okay. Sorry about the beeps there. That's just my computer saying it's about to restart. And I don't want it to restart. I want that to disappear off halfway into my lesson. I don't want it to update my software. I'm just going to ignore that. Hopefully it will go away. Because it's right on top of my notes that I'm doing where I've got this. Okay, so we know that theta 2 is going to be less than theta 1 because it's more dense. We're going to use Snell's law, which is n equals sine theta 1 over sine of theta 2. That's on your relationship sheet. And I would advise that you put the numbers in. You get a mark in tests and exams for writing down the formula just by copying it off the formula sheet. And you get a second mark for putting in the numbers. 2.42 is equal to sine of 10 degrees over the sine of theta 2. I ought to say at this point, I don't think this is so much of a problem with fifth years, but there are two ways of doing degrees on your calculator, or two ways of doing trig function sine. You can either use degrees or you can use something called radians, and I'm not sure how often you use radians in maths, but if you've come from doing a maths problem in radians and you then start putting in angles in degrees in your calculator, you're going to get completely the wrong answer. You must make sure when you get your calculator out that it actually says degrees. I'm just having a look at mine and it doesn't actually say degrees, which is a bit of a problem, but you're going to have to make sure it's set up in degrees. Some calculators say it's in degrees, it says DEG at the top, and some calculators will tell you it's in radians, but you need to make sure it's in degree mode or you're not going to get the right answer there. Right, so you can rewrite the formula, you can do some cross multiplying, do whatever it is you normally do. I might go from there to there, and then I'm going to go over here because I haven't got this. I should really be working down the page, but never mind. Sine theta 2 is equal to sine of 10 degrees divided by 2.42. There's nobody says you have to show every step in your working, and I'm not saying that you need to copy down what the sine of 10 degrees is and then divide it by and show it as being divided by 2.42. You can just do that in your calculator, put in sine 10 degrees, divide by 2.42, and you get 0.0 718. I'm not carrying these numbers around in my head. I've got a separate set of notes here. So what do we do then? We do theta 2 is the inverse sine of that number, 0.0718. And you do the inverse sine. You know where the inverse sine button is on your calculator. It's the shift sign button. And you get 4.1 degrees, and that's your final answer there. So there's an example which you'll need to copy down. There will no doubt be other examples, excuse me, or problems that you need to do in Campbell-Robertson, and there will certainly be some of these problems in the refraction block test when you eventually get round to it. I've already posted that up and the solutions, I think, so that's fine. What else can we do with that? If we replaced the diamond with glass, what would we get? And this would be a typical question, is you could estimate. Estimate means you don't actually have to do the calculation, but so part 2 could be estimate what would happen to that angle if you replace diamond with just plain glass. So this is part 2 of the question, and it's an estimate. There's no reason why you couldn't do a calculation to back this up, but what they're really looking for is for you to do some writing. Estimate the angle in glass when the diamond is replaced by some glass. Obviously it's in glass, it's been replaced by some glass. Okay, and and you need to do some explanation. You need to justify your answer or explain. You need to look at these command words. We'll be doing more on command words later. There is a list of command words in the resources sheet that says exactly what you need to do. So explain your answer. And if you don't explain your answer, you're not going to get the marks, even if your estimate is correct. So you're going to have to do some sort of estimate of what's going on. Right. So how do we do that? We know that glass is, so this is what you're going to do, something like this. Glass is less dense than diamond. It has a refractive index N that is less than 2.42. And we know what the refractive index is. It's for glass, it is 1.5. And N, refractive index G for glass, is 1.5. Now you know what's going to happen here, because we did this in lesson 1, is that the refractive index is a lower number, then it doesn't bend as much. So diamond really does bend the glass, bend the light. Start again. Diamond bends the beam of light in diamond by a lot. So this in diamond we worked out to be 4.1 degrees. We know that the refractive index of glass is only 1.5, so the beam of light doesn't get bent as much. So if you replaced this here in this original drawing with glass, N is 1.5, it doesn't bend the beam of light as much, so you're going to have, that's not even a very good drawing, is it? The beam of light still, it doesn't go straight on. It doesn't get bent as much, but theta 2 is going to be a bigger angle. So theta 2 in glass would be bigger than that angle that we got in diamond, which was 4.1 degrees in diamond. And you could make a rough estimate. You could say, okay, look, I can compare 1.5 with 2.42, and it's not quite half of 2.42. It's a little bit more than half. So perhaps this angle isn't twice as much. It must be a little bit less than twice as much. So my estimate is the angle is probably, no, it's not as big as 8, it's probably about 6 degrees. So we'll say 6 degrees. It is an estimate. You don't have to do an estimate to lots of decimal places. Now you could, of course, go back and actually work it out. There's nothing to say you don't have to work it out, because then what you would do is you would do N equals sine theta 1 over sine theta 2, and you'd have 1.5 equals sine of 10 degrees. That's the angle. Angle going in still the same. Sine theta 1 still the same over sine theta 2. You would swap those over just the same as before. Sine theta 2, sine of 10 degrees divided by 1.5. You put that in your calculator. I could probably do that right now. And I've just worked that out, and it comes out to 6.7 degrees. And I hadn't worked this out before, but you can use that logic of saying, well, what's the comparison between 1.5 and 2.42? It's not quite, 2.42 is not quite twice 1.5, so the angle is not going to be quite twice. It's not going to be as big as 8, and you can estimate it's 6, and it actually comes out to be 6.7, which is good enough. If you wanted to do the calculation, that's fine, just to justify your answer, then that would be good. That's not a problem. Okay, let's move on from that. Now, so far we've been looking at what happens if light travels from air into glass, or air into water, air into diamond. What happens if we use two different materials? And I've got, for instance, glass, and I've got water, and air doesn't come into it. So I've got glass. My glass has my refractive index of 1.5. My water has a refractive index of 1.33. Here's my normal line with water over there, glass over there. What would happen? Just to make it a little bit more difficult as well, I'm going to have my beam of light coming in here, and I'm going to say that this angle here is 50 degrees, and the beam goes off like this. And I know that this is theta 2. Now, I'm hoping what you're going to notice here is you're going to say, oh, Mr. Ford, you've gone and put the angle in the wrong place. This is a typical, I won't call it a trick, but it's just an extra bit of knowledge that you have to bring into the question. Is that's not the angle we want. That is not theta 1. Theta 1, these angles are always measured between the ray of light and the normal. Well, that is between the ray of light and the normal, but this is not between the ray of light and the normal. It's between the ray of light and the boundary. So there will be questions where they give you, if you like, the wrong angle, and you've got to work out what the correct angle is. Well, you've already know, I've mentioned this before, you already know that this is 90 degrees. So 90 degrees take away 50 gives you 40 degrees there, and theta 1 is 40 degrees. Theta 1 is not 50 degrees. Okay, so the first thing you want to do is calculate. It may not ask you explicitly to do this. You may just have to notice that that's the wrong angle and use it in the sine theta 1 over sine theta 2 is n. But I'm going to say, right, calculate theta 1 for light in glass, and you do that by writing theta 1 is 90 degrees, take away 50 degrees, and that is equal to 40 degrees, because theta 1 and theta 2 is always measured between the ray of light and the normal. Okay. Now let's go back now to have a look, and this is going to form part of the next bit of the question, but let's just go back and look at Snell's law. I'm going to rub that out for now. I've got the formula n equals sine theta 1 over sine theta 2. But this Snell's formula only has one value of n, and our example that we're looking at actually has two values. It's got whatever it was, 1.5 and 1.33. So we're going to have to change the formula slightly. I'm going to introduce you to a new formula. This formula is not on the sheet, and you're going to have to remember this, that wherever you have sine theta 1, you have an n1, and that is equal to n2 sine theta 2, and this is for two different materials. Okay, now if this was air and glass, here, then this would be theta 1, which is the angle in air, and this would be the refractive index of air, and the refractive index of air is simply 1. So you can get rid of the n1, and then you go back to having, that would go, and then you'd go back and you would have sine theta 1 divided by sine theta 2 equals n2, which is the refractive index in the material. So if you followed that, all well and good. If you haven't really, what you need to do is remember that if there are two different materials with two different refractive indices, you have two different angles, and you have to use this slightly amended formula. Okay, so this is material 1 or medium 1, and this would be the glass, and this would be the refractive index and the angle inside the water. So if we've got that question and it's disappeared off my board, I'm just going to have to go back and look at that again. I've got theta 1 in the glass, where n, you don't need to get all this down again. It's just to remind me and you what you can see on the screen. You'll have it in your book. Glass n is 1.5, water, or 1.50, n is 1.33, and I've got the beam of light coming in there. There's my normal. Okay, and it goes off up there, and this is theta 2, and we know that theta 1, because we've already done part 1, we know that theta 1 is 40 degrees, and we know that theta 2 is the angle we have got to find, and we know that n is 1.5 for glass and n is 1.33 for water. So we know three of the things. We know three of the variables in this formula. The only thing we don't know is sine theta 2. So I'm going to put in my values here. N1 goes with theta 1. N1 goes with theta 1. So I've got 1.50 times the sine of my correct angle, 40 degrees, not the 50 that you might have thought it is. And that is equal to, for the second material, 1.33 times sine theta 2. So I've got my formula. This is a bit more advanced. The formula is not given to you. It's definitely a problem-solving sort of thing. 4 variables, 3 known, 1 unknown. We can do 1.50 sine 40 divided by 1.33 is equal to sine theta 2. I can put all of that in my calculator, which I've done already, and I get 0.725. So theta 2, that's sine theta 2. So theta 2 is the inverse sine of 0.725. So you put 0.725, find the inverse sine, and that is equal to 46.5 degrees. So there's a second worked example for you there. Okay, now that seems to make sense because water got a smaller n value. Water is less dense than glass. If remember, the refractive index number is lower, the material's less dense, and therefore it doesn't bend the ray of light as much. So you'd have a larger angle. So here's your angle, which we already knew was 40. So this angle has definitely got to be bigger. It's 46.5, purely because of the difference between the two refractive indices. Okay, there you go. Let's move on. Well, in fact, I think I'll stop there. I'll stop this video, which is entirely of Snell's law, and then the next video 3, will be taking Snell's law a little bit further. So I'll pause this just now and go and do the whole compiling with Google Meet, downloading, uploading back to YouTube. I'll post up both videos in another post. So this will be video 2, Snell's law.